chapter 5. The chapter 5 is on energy coming out of combustion. We're going to talk about a lot of things in here, about fuels, what type of fuels are available, and what is combustion, and about energy. So basically, we are going to look at units of energy and various aspects of energy in this chapter. So let's go to the next slide. Fuel is anything that releases energy when we burn them. The way electricity is created is we burn fuel, the coal, gasoline, diesel, etc., to generate electricity, turning a turbine mainly in power generation. So in the picture on the top, you see an oil well that drawing crude oil out of ground. That's crude oil being distilled into various portions of fuels, gasoline, jet fuel, diesel, kerosene oil, and etc. What are the environmental implications of obtaining fossil fuel? They cause pollution even during transportation and even during burning. There are a lot of environmental implications of using fossil fuels that we're going to address in this chapter. So there's another alternative to using fossil fuel which are not renewable, which is biofuels, which are created and constantly, and we can consider them as renewable. So we're going to look into biofuels like methanol and biodiesel in this chapter. Energy, how it's used. For example, if you drive your car across the United States from New York City to Los Angeles, a distance of 4,460 kilometers, which is roughly about 3,000 miles. One mile is 1.5 kilometers. And the vehicle you are driving gives 30 miles per gallon of gasoline. How much gasoline would you need for this trip? 3,000 miles divided by 30 miles, you get 100 gallons. That's roughly the amount. Now imagine that car you are using is capable of using alternative renewable fuels such as biodiesel and ethanol. Using ethanol is less efficient than using gasoline. The ethanol burns at lower caloric value, that means low amount of energy given out burning ethanol than gasoline. When using ethanol, you can achieve only 20 miles per gallon, whereas 30 miles per gasoline. Many gallons of ethanol would how many gallons of ethanol would you need to cover the entire trip? So ethanol is 20, then 3,000 divided by 20, you get 150 gallons. So you need 50 gallons more of ethanol. Currently, ethanol is used for fuel predominantly made from corn. Assume it takes 26.1 pound of corn to make 1 gallon. A 1 acre of land produces 7,110 pounds of corn. How much land is needed to produce sufficient energy to fuel your trip using ethanol? That you have to understand 150 miles gallons need 150 acre land. So there are a lot of issues using energy, alternative energy. We're going to talk about in this chapter. Let's talk about fuels. Fuels are any solid gas, liquid that can be combusted to produce heat and work. Fossil fuels are formed millions of years ago from decaying plant matter. Once plant leaves, it goes underground. As time goes on, they decompose, partially decompose with heat, pressure, in the absence of oxygen, to coal and petroleum and natural gas. The process that plants form this organic material is through photosynthesis. Photosynthesis is a process where carbon dioxide and water react to form carbohydrate, mainly glucose and oxygen. So that's the endothermic. It requires energy. Energy is consumed. However, in the metabolic process, metabolism, glucose is burned in the cells using oxygen and produce carbon dioxide and water. And in that process, energy is released for our biological activities. That's the exothermic reaction. So decay and combustion have same overall reaction as metabolism, but the reverse. So this is the fuel we use mostly. Glucose, precursor to many gallons of fossil fuels and coal. And we, as a food, we can burn it in the cellular respiration to produce energy. Combustion is a general process where a fuel is oxidized, using oxidizer to produce products and release heat. There are three things in a requirement of a fuel: oxidizer, and heat. Majority of fuels are hydrocarbons, like gasoline, natural gas, propane, etc. Hydrocarbons are compounds made up of carbon and hydrogen and carbon, hydrocarbon. So they burn in oxygen. Oxygen is the oxidizer to produce carbon dioxide and water. In hydrocarbon, carbon atoms make 4 bonds to other carbons and hydrogen atoms in the molecule. Carbon shares total of 8 electrons, or 4 electron pairs, make 4 bonds. Sometimes carbon compounds make double and triple bonds shared between carbon-carbon atoms. And a hydrocarbon can be represented as shown in the right side. The first one is called structural formula, where the all carbon-hydrogen bonds are shown, and the second one is also structural formula. The third one is condensed structural formula. where the carbon-hydrogen bonds are shown in an abbreviated form, CH2, CH3, etc. And the last one is called line angle formula. Fourth one is called line angle formula, where only the carbon-carbon skeleton is shown. So there are other various forms of condensed formulas given in fifth one and sixth picture in the diagram on the right. So you need to be looking at hydrocarbons and recognize them using these representations. We already talked about hydrocarbon names. There's a mnemonic that you can remember to name first four hydrocarbons. Mother eats peanut butter. Mother means methane, ethane. Peanut butter means propane. Eats means eth. But means butane. You add the suffix to methane, ane, ethane, propane, ane, butane. Use this or any other memory aid of your choice to remember names of hydrocarbons, to tell how many carbon atoms are there in these compounds. Ethanol is also an organic compound which contains addition to carbon, hydrogen, oxygen as well. Ethanol is a component of beverages and a gasoline additive. Ethanol produced from corn is used as a gasoline additive. Methylene chloride is a carbon, hydrogen, and chlorine compound. There are two chlorine in the methane replacing hydrogen. It's used as a paint stripper and possible cause of possible indoor air pollutant, and it can affect the greenhouse gases too. Act as a not a greenhouse gas. Act as an agent for destruction of ozone layer, just like CFCs. They contain chlorine. Propane is a major component in liquid petroleum gas we call LPG, which is used in gas grills, etc. So I'm summarizing here names of hydrocarbons based on number of carbon atoms. Methane, ethane, C2H6 is ethane. How do you get the hydrogen number knowing the carbon number? Is 2n plus 2. 2 carbons times 2 is 4 plus 2 is 6. So you should be able to get the formula of hydrocarbon in knowing the number of carbon atoms. So as a fuel, hydrocarbon react with oxygen, produce carbon dioxide and water. So you need to understand how to balance also chemical reaction. We done that in previous slides. The fuels also contain variety of hydrocarbons, contaminated and other sulfur compound that produce pollutant when they are burned. This reaction is actually assuming fuel is consists of mainly butane. At high temperatures, nitrogen from the atmosphere also react with oxygen while burning fuel produce heat to get the high temperature and cause nitrogen oxides to form. That cause pollution releasing nitrogen dioxide to the atmosphere. So this is your turn to balance reactions. So if you are given C6H12O6, write a combustion reaction for that. That's balance, how you balance. So you count the carbon atoms on the left side of the reaction and carbon on the right side of the product side of the reaction, and changing the stoichiometric coefficients, you achieve the balance. For methane, there's a balance equation given. In all burning reactions of hydrocarbons and glucose, energy is released. That means exothermic. Exo means release. So go back to section in chapter 2 for information on balancing equations. In this chapter, we're going to talk more about energy. There are various forms of energy available in the universe. So mechanical energy, nuclear energy, chemical energy. So part of the mechanical mechanical energy is capacity to do some work. Work is measured by moving a force through a distance of certain distance given in the bottom here. Potential energy is due to position or composition of material. For example, in this waterfall, on the top of the fall, potential energy is high because it's placed high above the ground. At the bottom of the fall, the potential energy is reduced and it's converted to kinetic energy. Constantly, energy is converted from one form to the another. So there are transformation of energy. We're going to talk about that in later slides. Work is movement against a force. Work is measured by multiplying force and the distance traveled by the object. One of the forms of energy that we use is heat. We use heat to do many things in our household. Heating food, heating the room, and what else? Lighting and all that. Burning candles, right, like that. Heat is energy that flows from hotter to cold object. That's one characteristic of heat energy. It flows from hotter to cold through various ways. Conduction is one of the ways. The moving atoms vibrate, hotter atoms vibrate faster and transfer that energy to nearby atoms or molecules, and transferring energy across hotter to colder object. Temperature, the heat is really related to temperature. If you look at with high temperature, the molecules are vibrating faster. That means they have higher kinetic energy. So, as a rule, temperature is a measure of average kinetic energy of atoms and molecules. How we tell the temperature? There are various scales we have used to show units of temperature. One of them is Celsius, other one is Fahrenheit, and the Kelvin temperature. Commonly used are Kelvin and Celsius. So how do we tell the temperature? We use a thermometer, which is calibrated for scale, calibrated by dipping it in freezing water and melting water and melting ice and water and boiling water, which is 100 degrees Celsius. Freezing is take place at 0 degrees Celsius. Between 0 and 100, we have scale marked by 2 10 scale points. So you should be able to convert. We have done that in previous chapters, how to convert Celsius to Fahrenheit, Fahrenheit to Kelvin, Kelvin to Celsius, etc. There are various forms of energy. For various forms, most common unit of energy is joule. Mostly for heat, we use calories, so which are little differently measured. Calories measured little different from the joule. Joule is the amount of energy required to raise a 100-gram object by 1 meter against the force of gravity. Another unit used for heat is calorie. A calorie is the amount of heat required to raise temperature of 1 grams of water by 1 degree Celsius. These two are the most common energy units. For joules being the most common, normally calories are used when direct heat measurements are taken against temperature. So these are the conversion factors. 1 calorie is equal to 4.184 joules. 1 kilocalorie, kcal is equal to 1000 calories. A dietary calorie is labeled 1 big CAL, dietary calorie. It's really 1000 calories or 1 kilocalorie. So in the food labels, what we have is calories are dietary calories. So this is something that you should have been able to do. A slice of pizza contains 217 kilocalories, so 217 calories, dietary calories. Express this in kilojoules. So conversion factor is 4.184 10 to the 3 joules equal to 1 calorie. So then if you multiply 217 by 4.184, you get 907, big number that converts to kilojoules, 970 kilojoules. So that's the amount of energy you convert that from that piece of slice of pizza, 907.3 kilojoules. Now, to give you another perspective, calculate how much energy is expanded 1 kilogram book you lift to a shelf of 2 meters off the floor with the amount of energy from one slice of how many you could lift. This calculation is not complete. 1 kilogram is about 0.82 calories. So I think it's in a way it's complete. This to move 1 kilogram books 2 meters off the floor, it takes 0.82, but the total pizza produced 217 calories. So there are so many books, maybe 1,000 books you have to move to burn all the calories you ate. So in doing these calculations, you have to simplify the assumption made in doing the calculation in part B, like we done in the problem solving. So assumption was that you need to burn a lot more, you need to do a lot more work to burn calories than number indicate. So certain things take up very small amount of calories, physical exercise. Based on an assumption, is your answer too high or too low? This answer to these questions seems to be in agreement. In this slide, we're going to compare energies for various processes. So if I make it bigger, energy needed to heat the entire volume of water on Earth by 1 degree, that's a global warming. That's a lot of energy, 10 to the 24 joules of energy. Total amount of worldwide energy consumption, 10 to the 21,000 times less. Energy released by earthquake of 8.3 magnitude. That's getting smaller now. Energy from an atomic bomb is 10 to the 12. Energy content of a barrel of oil, 10 to the 9. Barrel of oil has 42 gallons of crude oil. 10 to the 6. Burning a 100-watt bulb for 5 hours. So that we are getting smaller and smaller. As we go down, we go to atomic scale. Energy required to separate a proton from neutron in atomic nucleus. That's very small scale. So then going down further, energy content of single sugar molecule is very low, but we don't eat one sugar molecule at a time. We'll eat a bunch of them. So therefore, there are a lot of energy in a grams of sugar. Average kinetic energy of oxygen molecule at 25 is very low, but that's only one molecule at 25 degrees Celsius. So you get the idea about range of energies that are possible. You guys over there doing all right? Are you guys there?
Yes.
All right. So water plays a special role in transferring heat from ocean to atmosphere and to the wind and things like that. It's attributed, this importance is attributed to higher specific heat water has. Specific heat of water is 1 degree Celsius. Calorie one calorie per gram per Celsius. A lot of energy required to change the temperature. Moisture stores heat energy. So once you cool down or heat, release energy from water, there's a lot of energies exchange. Heat of fusion is for water is energy release when water freezes to solid. So this phenomenon is used to prevent freezing of sugar of orange plants during the winter. They spray water. Heat of vaporization is when a gas condenses into a liquid. Huge temperature swing during the thunderstorm. So when thunderstorm happens, gaseous water is condensed to rain. Rain is liquid. So therefore a lot of energy is released. Then before bad weather, thunderstorm, you feel hot temperature increasing in the outside. So water takes heat to break intermolecular forces which are called hydrogen bonding, which take place during these phase changes, gas to liquid, liquid to solid, etc. When we measure heat changes, mainly, we use an instrument called calorimeter. Calorimeter is a device we use to measure quantity of heat released in a combustion reaction. Combustion reaction is burning with oxygen. So we put that inside the calorimeter and burn it. And calorimeter absorb heat from the combustion reaction and temperature increase. Related to this temperature increase, we can calculate the amount of heat given per mole or gram of the substance. So this increase in water temperature is used to calculate the amount of heat produced by combusting material. Heat absorbed is equal to heat release. That is used to as a calculating principle from calorimetry. We talked about exothermic reaction previously. When burning fuel can be compared to waterfall. So these two pictures are burning fuel, methane, and on the top picture it's waterfall. You can see potential energy in the bonds of methane and oxygen are much higher than the released carbon dioxide and water. Potential energy is in the chemical bonds that breaks up during the reaction and produce new bonds. The difference is energy is released as heat. That's the exothermic reaction. The combustion of methane gas releases 800 to 0.3 kilojoules of moles of energy. This is equivalent to 50.1 kilojoules per gram. So you can use grams to mole conversion to get given the heat of combustion in kilojoules per mole to get heat of combustion in kilojoules per gram. So this is commonly done in converting mole heat of combustion in kilojoules could be converted to heat of combustion of kilojoules per gram. Now, if you look at these potential diagrams for different fuels, methane, octane, coal, ethanol, and wood. Wood has the lowest, and ethanol, coal, octane, highest is the methane. So when you have, there are a few generalizations that you can make. As the ratio of hydrogen to carbon decrease, the heat of combustion decrease. Ratio of hydrogen to carbon. So as the carbon number increase, it goes down, like methane to octane. And also amount of oxygen in the fuel increase. So for example, ethanol to wood also, coal to wood, coal to ethanol, or methane to ethanol, the heat of combustion goes down, the potential energy decrease. So there are some generalizations about heat of combustion. Now we talked about exothermic versus endothermic reactions. Endothermic reactions absorb energy. Photosynthesis is an endothermic reaction. We talked about it. It requires energy. Potential energy of the product is greater than potential energy of reactants. On the exothermic reaction, potential energy of reactants are greater than potential energy of products. So when you're thinking about potential exothermic, endothermic reactions, the reaction system where the combustion takes place is called system. System release and the rest of the surrounding universe, the rest of the universe is called surrounding. In the exothermic reaction, energy is released to the surrounding. In an endothermic reaction, heat is absorbed by the system from the surrounding. So there are two consequences of, these are the consequences of endothermic and exothermic reaction. The energy changes take place at molecular level. Those potential energies are related to bonds in the fuel and bonds in the carbon dioxide and water. In the products, in the reactants, bonds breaks. They require energy. In forming bonds, release energy. When you make products, bonds are formed. We assume all the bonds are broken and reformed after the reaction. No net change is energy increase. Net change in the energy indicate whether the reaction is endothermic or exothermic. Bond energy is bond break requires more energy than bond release. From energy release from forming bonds, that means endothermic. It requires to more energy absorbed. Other way around is exothermic. Generally, bond breaking always requires energy. Bond forming process always release energy. In the diagram here in the slide, bond energies of different compound between different atoms are listed, cross-listed. For example, if you ask what is the bond energy of hydrogen bond, H and H, 436. Carbon-carbon single bond, 356. Carbon-hydrogen bond, 416. You read the carbon from the right column, the left period from the left column, and the hydrogen from the horizontal top column, where the cross section is the bond energy. That's how you obtain bond energies for different carbon-hydrogen bonds. Multiple bonds are different from single bonds. They are stronger than single bonds. For example, carbon-carbon single bond is 356, carbon double bond is 598. Carbon-carbon triple bond is even stronger. Nitrogen double bond and nitrogen triple bond, and nitrogen triple bond has high energy. There are heteroatomic bonds and homoatomic bonds, so they have energies given here. This idea about bonds broken and bonds formed have the principle, have the basis for calculating heat of combustion for different hydrocarbons. For example, heat of combustion of propane. So we look at in the structure of C3H8, there are 8. If you expand the structure, there are 8 CH bonds, 2 oxygen bonds, double bonds in the oxygen, and 2 carbon-carbon bonds in the skeleton of 3 carbon atom, 2 carbon-carbon bonds. We add them up, multiply them and add them up, then total energy required to break the bonds is 65.30 kilojoules. So on the side listed are the bond energies of different bonds, CH, like that. It's obtained from the table in here. So we do for the products where the bonds are made, formed, carbon dioxide, 3 molecules. It contains 3 times 2, 6 carbon-oxygen bond, double bond, 6 times carbon-oxygen bond, added up to 4,818. So water molecule has 2 OH bonds each. That means 2 times 4 is 8 OH bonds, adds up to 37.36 kilojoules. So we add them all. The total energy generated of release bond making is 8,554 kilojoules. So now bonds broken is positive, they require energy. Bonds formed is, bonds made is negative energy, release energy is negative. So when you add them, these numbers, positive 6,530 minus 8,554, the total energy is negative 2,024 kilojoules. That's the heat of combustion of propane. That's how we calculate different heat of combustion of different hydrocarbons using bond data. We had to do another problem. It's burning acetylene, CH, triple bond, carbon, hydrogen. That's called acetylene. When you balance the equation, that 2 acetylene molecules react with 5 oxygen molecules to produce 4 carbon dioxide and 2 water molecules. Now, like in the previous slides, we had to calculate bonds broken and bonds formed. Bonds broken are 4 hydrogen carbon bonds, carbon hydrogen bond 4. There are 2 carbon hydrogen in the molecule and there are 2 molecules, therefore twice that amount, 4 carbon hydrogen. And 1 triple bond, carbon-carbon triple bond, 2 of them, 2 triple bonds. 5 oxygen or double bond, OO double bond. So summarize this in the next one. I got the data from carbon-carbon bonds like that. So 4 carbon-hydrogen bonds broken plus 2 oxygen, 2 carbon-carbon triple bond, 5 oxygen bonds added up to 5805 kilojoules. So bonds made is 8 CO bonds and 4 OH bonds. That's bonds made is negative 8260. So overall total energy generated is, adding them up, 5805 negative 8262. You get the energy release exothermic. This is negative 2,455 kilojoules of energy release. Energy release means negative energy. So that's how you calculate energy values of heat of combustion of different organic compounds or fuels. Now we dealing with energy during the process of converting energy to different forms. There are a few principles that are governing these transformations. First one is called first law of thermodynamics. Energy is neither created nor destroyed, but they may be transformed from one form to the another. So that's a thermodynamic principle. It's called first law. Energy is neither created nor destroyed. If it is created then you can cyclically go back and produce more and more energy from nothing. Nothing could be produced from here. Energy should be there to be converted from another form. There also a second law of thermodynamics, that during energy processes, entropy of the universe should increase. That means randomness. That's universe get chaotic. You cannot have orderly system while producing energy. The total entropy, randomness, or created chaos in the process. When you burn fossil fuel, while energy is produced, it dissipates. Most of energy is dissipated to create thermal pollution and temperature increase in the surrounding, to creating more randomness than created. This energy loss due to randomness is called dissipated energy. In this diagram, you can see how a fossil fuel burning power plant works. So coal burning power plant. Burner full of coal heats up water in a boiler. Then they become steam, and the steam is sent through a turbine. Turbine is propeller turned by steam kinetic energy, and that kinetic energy is used to rotate a generator. Generator is electromagnetic coils going through magnetic fields, produce electric current, and then that electric current is sent to the population, large areas of where the energy is used, that's metropolitan areas. Then the steam is condensed back to water and resent to the boiler, and there's a reservoir of water, body of water. That warm water is cooled off and sent back to the boiler. So this process involves a lot of heat dissipation, thermal pollution in the water, body of waters. So that's according to second law of thermodynamics. It creates more chaos than order it produces. In the process, potential energy of the coal is released to kinetic energy. Kinetic energy of the steam are used to drive turbine. Turbine creates mechanical energy. Mechanical energy is used to feed the generator, rotate the generator to form electrical energy. There are various transformations of energies here. The efficiency of a power plant is defined as electrical energy produced, heat from the fuel. It's never 100%. It's mostly 40% efficiency. Therefore, a lot of heat is lost. No electrical power plant can convert one type of energy into another. Completely convert, only 40%. Some of the energy is transferred to use as useless heat. In general, higher the temperature of the steam, the more efficient the power plant is. So steam, to create higher temperature, it requires more energy. So I'm going